Daylight savings time is here. And well, we've got a bit of a couple days that are unseasonably warm in Michigan, so I thought I'd get out on my bike for the first time this year. Behind me there is my racing bike. Well, that's going to be on the trainer for about another month or so. So let's get out here my old mountain bike. And yes, I know I installed the handlebars upside down. Just trying to make it a little more aero. You know, mountain bikes really aren't about speed, but I've done some experiments over the last year trying to get as much performance out of this thing as possible. Before I get outside though, I've got some fancy toys that are worth about 20 times the value of this bike to stick on here, and we'll go from there. That wasn't a half bad ride for the first one outdoors anyway. Let's take a look at how we can use some math to analyze our performance and also to set some reasonable goals for the sport of triathlon. When it comes to calculating power on a bike, the math is not too difficult. But without a wind tunnel, we have to estimate some values based on commonly available information. More on that when it matters. However, I find, compared my math with what I get from my training gear, my results are within about 5% of reality, and that's pretty good. So let's start by taking a look at the overall equation. Power times the efficiency of your bike equals velocity times everything opposing you. From this point on, we're living here in metric land. I know it's going to trigger some of you here in the United States, but that's just kind of how this math works. Also, as long as you have not rode your bike for 900 miles without proper maintenance, we can ignore that efficiency value at the start of the equation and just kind of remove that. Which, on that topic, yeah. Now that I'm back on a proper maintenance schedule, let's look at a new equation. Power is equal to velocity, and then the everything opposing you has now become rolling resistance plus air resistance plus hill climbing plus wind opposition plus rolling wheel aerodynamics. Now before this seems all too overwhelming, we can ignore some more things. If you are riding on a course that starts and finishes in the same spot, hill climbing and wind opposition tends to end up close to net zero. Yeah, in reality land it doesn't, but it's close enough for our math. It's therefore fine to ignore these for most rides, and they're not too useful for today's tests. Rolling wheel aerodynamics do matter for triathletes. That's why top competitors spend over $4,000 on a full disc carbon fiber wheel in the back. However, we can just approximate those kind of upgrades in the air resistance parameter, so I'm throwing this one out as well. Let's break down the rolling resistance section now. So this part of the equation is about overcoming friction, and is equal to gravity times the coefficient of friction of your tire on the road times the mass of your bike setup with you on it. The only parameter we need to estimate here is the coefficient of friction. For a racing tire, we are looking at something around 0.003. However, if you have knobby gravel bike or mountain bike tires on, this value could be as high as 0.01. In metric world, gravity is 9.81, and it's going to be up to you to figure out the mass of your bike. Be sure to calculate not only the bike, your gear, but of course yourself as well. That's kind of the major bulk of it, after all. Now remember that 1 kilogram is about 2.2 pounds, and in my case, my total setup is going to be about 90 kilograms. Therefore, my first parameter for rolling resistance is about 2.65. Now let's talk about aerodynamics and cutting through the air. This part of the equation is equal to 1/2 times the density of air times CDA times velocity squared. The density of air parameter is something you can look up for your elevation. Here in Michigan, I'm training at about 700 feet above sea level, and therefore my value is 1.13. Velocity squared is the speed you are traveling at the moment. We'll plug in values for that a bit later. Now the thing called CDA, this is your aerodynamics parameter, and it breaks down into two things. The first being for your body, and the second being for your bike. In both cases, it is equal to the frontal area of either your bike or your body times its drag coefficient. For your own drag coefficient, it's impossible to figure this out without a wind tunnel. However, if you are wearing a standard triathlon kit, 1 is a pretty good estimate for your coefficient of drag. If you got something looser on, let's say a mountain biking kit or something, you might be looking at a value closer to 1.3. Moving on to the drag coefficient of your bike, a good estimate is going to be 0.88 if you're rocking some sort of racing bike. If you look around the internet for a while, you might be able to find the exact value for your bike, but it could be difficult. Manufacturers do know this number, but they generally don't release it to the public. Finally, you might have noticed the ruler sitting next to me here and that I'm now magically wearing my helmet. It's kind of important to have that on for this next step of the calculations. What I'm going to be doing to calculate the frontal area of myself as well as my bike, I'm going to take a picture of myself in several riding positions. We'll head over to Photoshop, and I'm going to be able to use this ruler as a reference to figure out the area of 1 pixel in the photo. And from there, I can expand out to figure out the total frontal area of both myself and my bike. I'm back in the studio to finish things up. Now I did the area calculations for 4 different positions. What I'm calling 1, the road position, which is a standard road bike position. I have an aero road bike position where I'm a little bit lower on the bike. I've got the future UCI cheater position, which by the time you're watching this may already be banned by the UCI. It was a position used by a pro cyclist fairly recently to win a couple races, and when the math shows why it works pretty well. And then finally I've got my Aero Bar Position, which on this bike is somewhere between a draft legal aero bars, which are going to be UCI banned I believe next year, and a more traditional setup for a triathlon bike. For my road bike position, I have my 0.88 coefficient of drag for the bike times the area, which is 0.1132 meters. Then I add that to my riding CDA with a 1 drag coefficient because of the clothes I'm wearing, and I times that by an area of 0.4077, giving me a total CDA for the road bike position of 0.5073. Now let's jump back to the fold equation, take the CDA, multiply that by the air density value, divide by 2, and then what I'm going to do to make life a little bit easier, I'm taking this velocity that's hanging over here, and I'm multiplying that out, so multiplying that with the rolling resistance coefficient value, and then also this entire mass that is the air resistance value. Then for the road position, I've got a final equation of 2.65 times velocity plus 0.2866 velocity cubed. Following that out for the rest of the equations, they all have the same 2.65 times velocity parameter because nothing over there depends on the position on the bike. It's all just other stuff. But for, say, the road aero position, we have an air resistance parameter of 0.2838 velocity cubed. UCI cheater down to 0.2436 velocity cubed, and finally for the aero bars we are down to 0.2388 velocity cubed. And there you go, those are the final set of equations I need to figure out how much power is required to go at a certain velocity. So at this point here you can either do some really crazy math to try to solve for velocity. No, just not worth it. It's much easier just to plug in known values for velocity for a given speed, and then you can just kind of approximate how much power you really need, because, you know, that's good enough for what we're doing here. So let's take a look at this screen to show you how some of that works. And because we're working in metric land, velocity is all meters per second. So I have a little chart at the top here. 18 miles an hour is approximately 8.047 meters per second. 20 miles an hour is 8.94 meters per second or so, and 21 miles per hour is about 9.38 meters per second. Go ahead and take each of these velocity values, plug them into those 4 equations I just showed a minute ago for each of my riding positions, and figure out the amount of power I need for a given speed. If I want to hit about 18 miles an hour in the road position, I'm looking at about 170 watts of power. Now that number is kind of important to me because at the moment that's kind of my estimated bike power for a 70.3 triathlon. I would like to get that up a little bit more, but I can't really guarantee it. 200 watts is not out of the question, but honestly I don't see myself outputting more than that for, you know, a nearly 3-hour-ish bike ride. Which the problem is, if I'm only doing 170 watts at about 18 miles an hour in the road position, that's a little over 3 hours on the bike, which is a little too slow for the goal I'm going for. However, if you look down in the lower right-hand corner with the aero bars there, 18 miles an hour is only about 146 watts, with 20 miles an hour being right around that 200 watt magic goal that I want to go with. Math doesn't lie. There's a perfectly good reason, as you see here, why all competitive triathletes ride aero bars. They're much more efficient than the row position. I mean, approximately, looking at my math here with my aero bars set up, you're looking at about 15% more efficient on those aero bars than you are riding the bike like a road bike. I knew this is the result I was going to get. I mean, going into this, I knew this was the result, but I figured I'd just confirm it anyway. The whole issue I got with aero bars, I'll tell you this right now, because triathletes don't tell you this until you've actually got one of these bikes. I call the thing death sticks for a reason. I've had a few oopsies on my racing bike, and they're all because of the aero bars. And they're all because trying to learn the aero bars. Now, the new aero bars I have on there right now, they're a little bit stubbier, like they're kind of extended length draft legal aero bars. Now, in theory, those push me back a little bit, so I'm sacrificing a little bit of aerodynamic performance for more stability, so maybe those will be a little bit less tricky to ride, but I'll find that out here pretty shortly. But, you know, it's very clear by the numbers I do want to learn how to ride those things. I know, that's how it's going to be, I guess. Anyway, thought we'd do a fun little math thing here. I like math. I know a lot of people don't. I like math, and that's why I do it on this channel every now and then. To kind of show you how you can use physics to figure out how to go a little bit faster to your bikes. Now, everything I showed you here today does apply to other types of bikes, mountain bikes, whatnot, your $50 grocery store bikes. And you can make changes like that, like as you saw me doing in the intro, to get a little bit more speed out of my mountain bike. Now, it's kind of funny for those who watch GCN, the April Fool's Day joke was actually putting drop bars on a mountain bike frame, which I actually did last year. It's not a good idea. Don't do it. They don't work. There's a whole story behind that. I had some custom 3D printed parts to hold the brakes and the shifters on. Bad idea. But what was so cool about it is I could predict the math changes as I added things to it, and it worked. It was so crazy. Anyway, that is about all I got for you guys today. So once again, I'm Jason, the creator of the Tabletop Battlefield. If you want to learn more about Team Hopewater International, who I'm riding with this year at Ironman 70.3 Michigan, I got to get that right. People are yelling at me. Put a link down in the show notes. And until next time, thanks for watching.